Okay, hello everyone. Today we want to talk about the issue named prompt overfitting. My name is Bong Xuan Jing and I will introduce the background and motivation. Traditionally, large language models are mainly used for text generation tasks such as summarization and question answering. Recently, researchers start using LLM as intelligence agents that interact with environments and make sequential decisions. In this setting, the environment is converted into a text prompt. The LLM select an action and reinforcement learning is used to improve the agent through the rewards and interaction. This allows the LLM agent to adapt to complex tasks such as planning, reasoning, and decision making. The problem is researchers found that these models are highly sensitive to prompt formulation. For example, if the word of the prompt changes slightly, the agent may choose completely different action even though the meaning is the same. This suggests that the model may memorize specific prompt pattern instead of truly understand the environment. The paper referred to this issue as prompt overfitting. This become a major challenging because real-world environment often contains diverse and unpredictable prompt variation. To solve this kind of problem, the paper first analyzed how sensitive the agents are to different prompt formulation. Next, the author measured the performance degradation caused by the prompt variation. Finally, they proposed a constructive regulation method to improve the robustness and help the model generalize better. The overall goal is to build a more reliable and adaptable LLM agent for interactive environment.
So thank you, Bong. And next, I'll talk about the core challenge for these journals is the prompt overfitting in RL trained LM agents. In the journal proves that the LM agent is just memorizing rather than learning. And even though they have a high performance to do some tasks, but it does not mean that the LM agents have a robustness intelligence. So next, during the LM agent building, they also have some challenges such as the interactive environments. Need to ensure the environment realism, also ensure the interactive actions, and also ensure that within the multi-step reasoning is stable. And for the reward designs of the RL, rather than only focus on the model performance, we're also considering the maintaining the robustness and generalizations as the rewards. So next, during the training, they also have some challenges such as the evaluation difficulties, because for these journals, it's aimed to also evaluating the robustness and prompt sensitivity, not only about the performance. So due to this project is an LM agents, the high computational cost also should be a challenge that need to be considering. So next, I will pass to Kok Wai to continue the presentation.
So my name is Scott White, and for the methodology, the author used a text-based reinforcement learning environment. In these settings, the LLM will act as an agent which receive a goal and observations in text form and then produce a text-based action. So the environment will then give a reward based on the agent actions. And the LLM agent is fine-tuned by proximal policy optimization or PPO, which help the agents learn better actions by maximizing rewards. And the main focus of the methodology is to test prompt overfitting. This means the agent may perform well when using prompt format seen during training, but perform poorly when the same information is presented in different prompt format. So to reduce this problem, the authors introduce a contrastive learning, which will encourage the model to create similar internal representations for different prompts that carry the same meaning. Overall, the methodology combined the PPO reinforcement learning and contrastive learning to improve the LLM agents' performance and robustness across different prompt styles. And for the data set, this paper does not use traditional fixed data set. Instead of, it used the interactive text-based environments, which is text, word, common sense, and baby AI text. And in these environments, the LLM agents receive text observation, goals, and possible actions, then choose actions and receive a reward from the environment. Therefore, the training data is generated through interactions called rollouts rather than collected from fixed data set. And next, I will pass it to Sean.
Hi, my name is Sean Kai, and in this study, the experiments aim to resolve three questions, which are prompt sensitivity, state representation, and impact of prompt information on action choice. To achieve this, Plan T5 and GPT-Neo models were trained using proximal policy optimization, or also known as PPO. They were trained on different scenarios, which includes training on a single prompt, training on multiple prompts, and also includes a contrastive loss approach. Next, to evaluate model performance, the fine-tuned models were compared against the zero-shot model on both seen and unseen formats, where the unseen format adds changes to names, context tag, and includes reordering. The metrics used for evaluation can be divided into 4 parts. The first is task performance, which is the success rate of the agent and the mean success rate across all prompt formulations and episodes. Then, hidden representations are evaluated using cosine similarity and UMAP mapping. Third, the relevance of prompt information is evaluated by calculating the average saliency of prompt tokens. Last, the knowledge acquired about the environment is evaluated by measuring accuracy in QA tasks, which includes object counting and task-related questions. That's all for my part. Thank you.
Thank you, Sean. My name is Ko Wong. Now I will explain the impact of fine-tuning the LLM in the interactive environments. So first is the prompt sensitivity. This figure shows the success rate of 3 models across different prompt formulation in 2 environments. In the TWC medium environment, both the FLAN T578M and 780M models achieve success rate exceeding 90%. However, there is a clear drop of more than 30% when moving from original P0 to the P3 variation in TWC medium, and similarly from the P0 to P2 in baby AI tests. And this lead to prompt overfitting, where the models learn specific wording instead of general task understanding. And next is the state representation. This table shows the inter and intra similarity comparison for 3 models on TWC medium. It can be seen that intra approach 1 while the inter is consistency below 0.5. This means the model group states more by how prompts are phrased rather than their actual meaning. And the UMAP is also used to visualize the hidden representation. It can be seen that no overlap is observed between prompt cluster even after the fine-tuning. This further shows strong prompt sensitivity that persists across training. And lastly is the usefulness of the prompt information. The figure shows that P1 focused more on inventory, while the P0 and P2 emphasize possible action. Even after fine-tuning, the attention patterns still vary, confirming that prompt wording strongly influences the model behavior. That's all for my part. I will now pass to Kai.
Okay, thank you, Kwa. My name is Kai. So previously, the paper discovered a problem called prompt overfitting, which after reinforcement learning fine-tuning, the LLM become too dependent to the exact prompt format used during training. Like when a prompt style changed, even if the meaning stayed the same, the model's performance dropped significantly. So the paper tests whether the contrastive learning could reduce this issue. And we can see that the result, it shows a clear improvement after applying contrastive learning. Like this table, it shows that all the model performs better with contrastive learning. For example, the FLAN T578M model, it improved from 0.77 to 0.92 success rate, which this means that the model could generalize much better to the new prompt style instead of memorizing the training prompts. In the question answering and object counting task, the model performs also achieve much higher accuracy compared to the normal reinforcement learning. So after applying contrastive learning, the hidden representation become more focused on semantic meaning instead of prompt formatting. And the model also pay attention more consistently across different prompt styles. So overall, the result shows that contrastive learning successfully reduced the prompt overfitting and also help to create more reliable LLM agents for interactive environments. And I'll pass to Susie. Thank you.
Hi everyone, my name is Lao Shuqi. So in conclusion, this paper shows that reinforcement learning can improve the performance of large language model agents in interactive environments, but the model will become highly sensitive to prompt formulation after reinforcement learning fine-tuning. So even small change in wording or formatting can significantly reduce the success rate, which is also called prompt overfitting. So to solve this issue, the authors propose a contrastive regularization method to help align semantically similar prompt in the latent space. But there are still some limitations in this study. First, the experiments are only conducted in text-based environment using limited prompt variation, so the result may not fully generalize to real-world ambiguous prompt. Moreover, although the proposed method improves robustness, it does not necessarily mean the model has deeper reasoning ability. It also increased the computational cost using reinforcement learning fine-tuning process and difficult to scale to larger model. So that's all for our presentation. Thank you for listening.